As I promised, we are going to improve traditional computer architecture. As you know, engineers squeezing performance from CPUs have a long, rich history. After turning up the frequency as much as they could, architects had to look somewhere else. One of the first places they found for improving performance was instruction level parallelism, or ILP. Think of ILP this way. We have a program that we need to execute. Everything is working well, but now we want the program to execute faster. If we don't change the system, in our case this funnel, our system will be overloaded. The catch? The funnel is the bottleneck. Well, we are going to change the funnel to make the program faster. We are going to look at instruction level parallelism using the ultimate ILP method, very long instruction word, or VLIW. You may be asking, what is VLIW? An architecture? No. An implementation technique? A machine? No way! VLIW is an architectural design philosophy. It is a set of informal guidelines, principles, and common building blocks that serve as a contract between computer architects and compiler writers. It exposes parallelism to compilers so that the compilers can generate highly efficient parallel instructions called very large instruction words. By the time you have finished this lesson, you will be able to answer the question, how does VLIW allow performance at a reasonable energy budget? Let us begin our lesson on VLIWs by first discussing how and where it evolved. Historically, RISC emerged in the 1980s as a reaction to what many felt was bloated and overly complicated ISAs. Talking about the RISC, they consist of simple operations plus load store for getting the data from the memory. As against that, historically the focus of CISC has always been on reducing the semantic gap between the programming and the hardware by combining lots and lots of instructions, the example being a string move, moving string from one place of the memory to the other, for example. We begin with a simplified diagram of the main memory, registers, and ALU for a processor. Let's see what happens when we perform a simple multiplication command, A is equal to A star B. Let us say there is a 10 in location 2, 3, and then there is a 7 in location 5, 2, as shown here. With the CISC architecture, then we can use a complex instruction to perform this task. The CISC programmer uses the command mult 2:3 5:2, and the result of the command will be stored in the location 2:3. In this case, the value is 10 times 7 is equal to 70. The RISC programmer, on the other hand, will have to perform a slightly different set of instructions to achieve the same result. The first step, load the value from location 2:3 into register A, as shown over here. Now the programmer needs to load the value from location 5:2 into register B, as shown by this load instruction. This value 7 is now going to get loaded into register B. Now that both the values have been fetched from the memory and stored in the register, their product can be calculated. The RISC programmer now uses the instruction prod A, B, as a result of which the value in A and B is multiplied together and the result is stored in A as 70. After computing A times B in A, now the final step for the programmer is to store the result in the main memory using the store instruction. The store 2:3A instruction takes the value from A and stores it back into the main memory at 2:3. This example shows the difference between CISC and RISC architectures. CISC hides the architecture from the programmer while RISC exposes it. The CISC instruction multiplication bx times ax is where the difference lies, which translates into 3 different instructions in RISC, 2 loads, multiplication followed by a store. Here are the differences between RISC and CISC design philosophies. In RISC, we have simple, fewer instructions, whereas in CISC, we have many complex instructions. In RISC, we have fixed length of instructions, which are typically very small. In CISC, because it could have multiple operands and variable number of operands, we could have variable length instructions. The complexity of RISC type of processing is towards the compiler. The compiler has become very smart. Whereas in CISC, the hardware becomes complex, so the complexity is pushed to the microcode or the hardware. In RISC, we only have loads and stores instructions, which can access memory, only 2 of those. Whereas in CISC, every instruction potentially could access memory to get its operands, so there are many such instructions which can access the memory. In RISC, we have few addressing modes, again because they are coupled with loads and stores. In CISC, we have many different accessing modes because each instruction could access memory, and for each one we could have different ways of accessing its operands. RISC versus CISC. What do you think? Which one is better? Well, the debate is over because CISC has been embraced by the industry quite significantly, especially Intel's x86 is all over the place, and which is a CISC architecture. But RISC also has its own place. The RISC is being used many times for programming at microcode level, and also RISC is being used in machines or processors such as MIPS, which are being used increasingly in many embedded controllers. Which of the following are CISC characteristics and which of them are RISC? So we have to write R for RISC and C for CISC. And the answer is CISC. The CISC instructions make more efficient use of slow memory. As each instruction can do more, few instructions are needed to perform a given task, and this leads to more efficient use of the relatively slow main memory. Okay, so the next question is, which one requires a less complicated compiler? And the answer is again CISC. CISC instruction sets can be written to match the constructs of the high-level languages. This means the compiler doesn't have to be that sophisticated or complicated. The next question is, the instructions take different amounts of time to execute. Is it going to be in CISC or is it going to be in RISC? And again, the answer is CISC. The reason the instructions take different amounts of time to complete in CISC is because of their variable length. And secondly, they go to memory, and memory can have different amount of latencies. Now let's talk about hardware. Is it going to be in RISC that we have simple hardware, or is it going to be in CISC? And this time the winner is, or the answer is, RISC. The simpler hardware is because of simpler instructions. Now let's talk about the cost of the chip. Is it going to be RISC or CISC, which is going to be less costly? And the answer is, it is going to be RISC. Because the chip is simpler, it also costs less. Lastly but not the least, if you have to write a program in RISC and write the same program in CISC, which is going to be a longer program, the answer is, it's going to be RISC. There is going to be a code expansion in RISC because each instruction is simple. We're going to need a large number of those. These different limitations of RISC as well as CISC in fact lead to VLIW. VLIW is an architectural design philosophy, and the key idea is to expose the instruction level parallelism in the architecture by applying it to the microarchitectural hardware, to the ISA or the instruction level architecture, and finally to the compilers. The idea of VLIW is to have multiple small instructions in one large instruction. For example, here is an instruction packet that contains 4 instructions, one floating point instruction, 2 integer instructions, and 1 memory instruction, all packaged into one large instruction which we call as VLIW. These 4 instructions will execute in one cycle in parallel and do different things, as you can see here. So let us understand the CISC versus RISC versus VLIW through a simple instruction. Here is a visual example of the instruction add 4R to R1 in a CISC, RISC and VLIW format. Here is a CISC version of this instruction. So the same instruction in RISC translates into 3 different instructions, one load followed by an add followed by a store. So here is a VLIW version of the same program. What we have done is we have put the load, add and store in different slots as a part of long instructions. Notice the number of empty slots which are present over here, but this is true only for this example. In practice, we'll be able to fill up many of these slots with other available instructions which are ready to execute. So why are we talking about VLIW all along? The main reason is VLIW is heavily used in embedded systems. Main reason why it has been used so heavily in embedded systems is because it has been a high-end processor, and it has also been a general purpose processor. It needs lots of transistors, but guess what? There have been lots of transistors in modern processors because of the increase in the transistor budgets. One of the issues about VLIWs is that it needs lots of transistors, but guess what? In modern processor, there are plenty of transistors we can draw from. And finally, we need a very powerful compiler for VLIW, and guess what? The modern compilers are excellent for extracting ILP and therefore can do VLIW processing very well. Like any architecture, VLIW has its own set of pluses and minuses. So one of the positives about the VLIW is that it has simple encoding and it has plentiful registers for holding the values. It has lower number of transistor budget than any other designs, and it gives you a better price and a better power consumption, and it has the scale efficiencies, which means that the cost per the transistors is also low. Let us now look at the drawbacks or limitations of VLIW. So VLIW architecture is not backward compatible, nor it is upgradable. However, VLIW is excellent for embedded implementation because rarely we want to keep the life cycle of an embedded device much more than 2 or 3 years and be able to upgrade or make it upward compatible and so on. Now finally, remember that VLIW is really an architecture and is independent of the implementation technique. So in other words, VLIW can be combined with the pipelining concept, it can be combined with simultaneous multithreading, and it can be combined with chip multiprocessor architectures. And all of these can be built on top of a processor which has a VLIW architecture. Alright, so far we saw 3 different concepts. One is RISC, another is CISC, and third is VLIW. Let's see if we can put those to work and identify which architecture is which one. So I'm going to give you 3 different diagrams and ask you to identify which is what. And the answer is CISC. So you see what is going on here? All those complex instructions are all being processed by the ALU, and that's why this particular architecture is a CISC architecture. You see no registers here, nothing else, and that's why this is CISC. Alright, now let's go to the second architecture. What's going on over here? The instructions are coming. There are a whole bunch of registers over here, and then there are different ALUs which are picking those instructions and executing. So what kind of architecture is this? Well, the answer is VLIW, because you see that there are multiple such processing units which are operating in parallel here and which are gobbling those instructions and executing those in parallel concurrently, and that's why this is a VLIW. Finally, what kind of architecture is this? Which is sending instructions, going through all those registers, but now you got only one ALU here. Obviously, this is a RISC architecture which mandates that each of the operands got to be in registers before the ALUs can use those. And that's why this is a RISC architecture. Let's now compare VLIW versus superscalar architectures, and we can compare them along multiple dimensions. The first question that we can answer here is which operations can be executed in a given cycle. Now let's look at the next question that needs to be answered before we make a choice between VLIW versus superscalar. One of the things that decides that is the issue of data dependence, and second is the issue of resource availability. Now these are not the only 2 questions, there are multiple other questions, especially concerning the power consumption and so on, but these 2 are the biggest guiding principles that decide the choice of VLIW versus superscalar. Let's now study VLIW versus superscalars in terms of different aspects that we talked about, especially the instruction scheduling part and the data dependency part. So in terms of the instruction scheduling part, in terms of superscalars, all the instruction scheduling is done by the hardware at runtime. And so the hardware is complex in that particular case. Whereas in case of VLIW, since the whole architecture is exposed to the compiler statically does the instruction scheduling, and so is the energy efficiency and the complexity of the hardware is low. In terms of the data dependency side, the hardware is the one which checks that for superscalars. In terms of VLIWs, the data dependency is checked statically by the compiler and enforced by scheduling the instructions properly. Both VLIW and superscalar begin with the same source code, of course, which is written in your favorite language like C, C++, which are the most important languages for embedded processors. We start with the same source code in both cases in terms of VLIW as well as superscalar. The superscalar compiler is a normal compiler which compiles the code for registers and so on. And the VLIW compiler is also a normal compiler, but it has additional parts, one for scheduling and secondly, one for packing those different parts of a big long instruction. So the normal compiler for a RISC processor will emit a code which has registers inside it and which will be a sequential code. Whereas as we saw for the VLIW, this particular compiler, which is also a compiler for scheduling as well as filling those slots, will generate wide instructions in which some slots are filled and some are unfilled. Now, having checked the compile time in terms of what happens in terms of different types of compilers, let's now switch gears and look at the runtime. On the RISC side or superscalar side, The scheduling and other operations are done by the hardware at runtime, and you can see that the hardware is doing a lot of work here. On the other hand, for VLIW, all that work is already done by the compiler, and the scheduling and filling the instruction sorts, it's already in place. So when the code executes, there's nothing to be done by the hardware. Now, in both the cases, as you can see here, however, we are getting the instruction level parallelism, but in two different ways. One is because of the lots of efforts by the compiler. In other case, there's lots of efforts by the hardware. And that's an essential difference between a superscaler versus a VLIW. So through that particular example on the last slide, we saw how are the different things between VLIW versus superscalers. Let's summarize that now. So VLIW typically needs less hardware and can be a low power machine. However, what you can see is, because the programs are compiled to execute in a particular order, the programs must be recompiled again even on small changes. As compared to VLIW, in superscalers, however, we have object code compatibility, which means that if the ISA is not changed, the same program can execute again and again because all the other stuff is done inside the hardware. So sequential programs can be presented to different superscaler implementation of the ISA and they just work fine. And that's one of the biggest benefits of superscalers, that we don't have to recompile those programs. So under the hood, we can change the architecture or the microarchitecture implementation in superscalers, and everything is just remaining the same in terms of the software. Whereas this is not the case for VLIWs, because if the architecture changes, the ISA changes, and therefore we must recompile the program again. So looking at these different trade-offs, you must be wondering that, hey, all the important work in terms of VLIWs is done by the compilers. And so we must need heroic compilers. Is that the case? That's a fallacy. In other words, the compiler has to be sophisticated, but there is nothing heroic about those as commonly misunderstood. We are going to have a quiz now between VLIW versus superscalers. So I want you to write S for superscaler and V for VLIW in each one of these different questions that we have. Let's start with the first statement. The hardware handles all register renaming. Which one does it? Is it superscaler or VLIW? Write your answer there. Let's go to the second question. A high bandwidth between the instruction cache and the fetch unit exists. Who does that? Is it superscaler or is it VLIW? The third question. The hardware tries to issue as many instructions as possible in parallel. The fourth one. The power consumption is large. And the last one, but not the least, a good compiler can detect parallelism throughout the whole program. So why DSPs are so popular in embedded systems? The main reason is, look at all the smartphones and in phones in general. Voice needs to be converted into the digital form and back to the analog form. And that's why DSPs are prevalent in every possible phone that we use, be it just a simple smartphone or a very complex one. And that's why DSPs are very common in every possible phone, from a very simple phone to a most complex smartphone. So DSP is a very complex device. It needs to work in real time. DSP is what we call as a special purpose processor, which is highly specialized to a particular job. It needs to work in real time to convert voice into digital form and so on. And so the performance is very important, and so is ILP. So the question is DSP more like a VLIW or is it more like a RISC processor? And the answer is, it is more like a VLIW because of power reasons. So what is the real difference between a digital signal processor and a regular VLIW? Well, the boundary is often fuzzy and the word is sometimes used interchangeably. As I mentioned earlier, many DSPs actually follow a VLIW design principle, for example, Texas Instruments C6X. There are some aspects of DSPs that can be adapted to VLIW, and then there are some other aspects which are not so obvious, which are unique to DSPs. So let's check all that applies from below to VLIW and DSPs. So first question is, multiple arithmetic units may require memory architectures to support several accesses per instruction cycle. Is that true for DSP processing? The second question is, simple SIMD operations can derive multiple arithmetic units in parallel. The last question that we want to address is, what about bit reverse addressing? What is bit reverse addressing? This is a special addressing mode useful for calculating FFTs. Let's address the first question here. Do we have a sense of multiple arithmetic units needing several accesses per instruction cycle in VLIW or DSPs? The answer to that is no. In VLIW, we do not allow multiple such accesses in one instruction cycle. Remember the VEX code that we talked about earlier? There is only one load or a store that is present in a given bundle. In DSPs, however, we could have such a requirement because we want to get all that processing done in real time. Let's look at the second question. Do we have a requirement of SIMD processing? That is, multiple instruction executing in one particular cycle. This particular aspect of VLIW is very useful in DSPs because we want to get lots of data processed in one cycle. Last but not least, what about bit reverse addressing, a specialized addressing mode? Well, this particular mode of addressing is peculiar to DSPs because it is extremely useful in fast Fourier transforms, which is at the heart of signal processing. However, this particular mode is not useful in general for other computations and so is not a part of VLIW. Now we are going to switch gears and talk a little bit about the role of compilers, and we are going to focus on the compilation for VLIW. In particular, we are going to focus on the phases of the compiler which are useful for scheduling and generating the code for packing a particular instruction word. Let us understand the structure of a compiler. So every compiler has what is called as a front end, which is language specific. For example, you could have a different front end for C, and then you could have another front end or a different one for Java. In spite of having different front ends for different languages, many compilers share the same middle end, what is called as a machine-independent phase of a compiler. What happens in the machine-independent phase? The intermediate form is generated, which is language-independent. Finally, we have what is called as a back end of a compiler, which will take the machine-independent representation from middle end and convert it into machine code. For embedded systems, the back end is one of the most important parts because it allows you to tune the code to a particular processor for which we are optimizing. Now let us understand the compilers for VLIW. What is different about them? Well, all of them do instruction level parallelism. So in that sense, it's like a normal ILP compiler. The compiler is supposed to produce high performance code. So what it needs to do is generate a lot of instruction level parallelism, and this is similar to the traditional high performance compilers. However, remember that we are compiling for VLIW architecture, and so the backend must understand the VLIW architecture and tune the code towards this VLIW architecture. So now let us understand at a high level what are the different optimizations that are done by this particular compiler for especially VLIW. One of the key optimizations is called as code reordering or instruction scheduling to capture the parallelism by spreading those instructions around and by arranging them in a particular order so that they execute the fastest possible way. This is one of the key phases for a VLIW compiler. And how does this really work? Remember, each VLIW machine is different. The number of instructions that could concurrently execute are different. Which operand they could access, whether they could access multiple memory locations, all that is different for different machines. And this is why we call these optimizations as machine-specific optimizations. What could be a good example of a machine-specific optimizations? In many embedded VLIW processors, the number of registers is different. Not only the number is different, the way the registers are organized is also different. Some of them are clustered, some of them are unclustered, some of them are inside a file, and so on. And so the register allocation is a very, very machine-specific optimization which differs from one VLIW to the other. So when you design such a machine-specific optimization which is closely geared towards the given architecture, what are the different design decisions you need to consider? What are the different questions that you need to address, and so on? One of the key trade-offs is called as phase ordering. Which to do before what? So for example, should we give the registers before we schedule instructions, or should we schedule the instructions before we do the register allocation? This is one of the trade-offs that is faced. So what are the other trade-offs here? The other trade-offs are all about resources. For example, there could be a trade-off between the amount of memory and its impact on register allocation. We could increase memory and reduce the burden on register allocation, or we could compact the memory and increase the burden on register allocation. We have been discussing the importance of scheduling in VLIW. In particular, let's now discuss the global instruction scheduling, which really impacts VLIW's performance in a little bit of a detail. So first of all, the global instruction scheduling is one of the key optimizations for exploiting the instruction level parallelism. So what is the key goal of ILP? The key goal of ILP and instruction scheduling is to find as many operations as possible which can execute in parallel. So now let us see the difference between the local instruction scheduling and global instruction scheduling. Local instruction scheduling typically just deals with straight line code without any control flow, any branches, none of those things. And so it is rearranging those instructions which occur one after the other in that straight line code. However, global instruction scheduling spans typically the whole program or a function, and there could be branches, there could be joins, there could be control flow conditions, and that's why it is much more complex. The local instruction scheduling has a limited scope because it operates on a small piece of code, but the global instruction scheduling operates on a large function or many times even can span across the functions and has much larger scope. So we have seen some basic principles of compiler design, and now it's time for a quiz. There are 3 statements which we are going to look at and see if they are true or false. So please mark the ones which are true with a check mark, leave the ones which are false. The first statement is VLIW code bloat is caused by the increased bandwidth between the instruction cache and the execution unit. The second statement is a VLIW compiler looks at a small instruction window. This increases the speed of compilation. And the last statement is VLIW CPUs offer significant computational power with greater compiler complexity than most superscalar CPUs. So now let's check our answers. The first statement was whether VLIW code bloat is caused by the instruction bandwidth between the instruction cache and the execution unit. That is false. So why is the VLIW code bloat caused? The main reason is because of what is called as a compensating code, which sits at the boundaries of the control flow to make sure that the right values are in the registers at the right point. And we'll be talking about this aspect later in the course. The second question is whether a VLIW compiler looks at a small instruction window to increase the speed of compilation. And the answer is again false. Speed of compilation is not really a major issue, and VLIW compiler must look at large windows to be able to find the maximum ILP. Now let's look at the last one. Whether VLIW CPUs offer significant computational power with a greater compiler complexity? The answer to that is absolutely yes. We do have a significantly higher ILP, but we do also need a pretty sophisticated compiler to be able to use that, and that's the hallmark of VLIWs. What we have here is 3 statements, and I want you to mark those which are true with a check mark in front of them. I'm going to read those right now, and you're going to then go ahead and mark those which are true. The first statement is compilers for embedded systems require a higher code efficiency than superscalar system. The second statement is compiler techniques for VLIW architectures can be fine-tuned by human assembly code programmers. And the third statement is compiler techniques used by superscalar architectures are readily portable to VLIW compilers. Please go ahead and mark your answers now for each one of these statements. The ones which are true, please put a check mark against them. The first statement, compilers for embedded systems require a higher code efficiency than superscalar systems. Is this statement true or false? This statement is true. Why is it? Superscalars need out-of-order processing and they heavily optimize the code dynamically, whereas in embedded systems, for the VLIW and other techniques, there is no such dynamic optimization, and therefore the compilers must require a higher code efficiency here. The second statement, compiler techniques for VLIW architectures can be fine-tuned by human assembly code programmers. This statement is false. The compiler has an ability to understand and optimize the code at a much higher level than human beings can because it can do a global analysis. The third statement, compiler techniques used by superscalar architectures are readily portable to VLIW compilers. This statement is also false, and that is because the superscalar dynamically optimize and reorder code, whereas VLIW is statically scheduled, and therefore totally different set of techniques must be developed here. Let us now summarize the characteristics of VLIW hardwares. First and foremost, the VLIW processors are simple, So there is less control hardware. There is no hardware, for example, for out-of-order execution here. Because the hardware is simpler, it is less expensive. Many of the VLIW processors also support some special purpose computing, and therefore it need not be general purpose and need not be tuned for performance across the board. And because the architecture is simple, it is easy to scale and customize compared to superscalers. Let us now look at the characteristics of the VLIW code. So first and foremost, the code is very predictable because it's statically scheduled. It also exposes a lot of instruction level parallelism. In terms of object code compatibility, let us see what are the different issues here. So first of all, this is not a major need in embedded systems, and so we can compromise this particular feature. Code is typically rebuilt and never reused on new products because a lot of things change from one generation of embedded systems to the next. And therefore, object code compatibility, which is difficult in VLIW, is not an important attribute which we should adhere to in embedded systems. In this lesson, we reviewed VLIW and compared it with RISC, CISC, and superscalar architectures. We discussed the benefits of VLIW, which were low price, low power, and size efficiency. And we discussed the trade-offs. It is not backward compatible, and the implementation details are exposed. You should have enough knowledge to answer the question I posed in the introduction to this lesson. Why is VLIW such an architecture of choice in embedded systems?